All right, how's it going, everybody? We are here on Tuesday, March 30th, and today we're going to be talking about section 8.5, probability. And as you see, I've got a block of text on the screen here. I really, really like this topic. I wish that we got to spend a little bit more than a day on it here. So I do kind of want to throw this out to you guys about how I think that you should be thinking about this topic. When I took Introduction to Statistics, it was during I guess it was like my fifth semester of college that I took Intro to Statistics. I think it was required being a math major. I had already finished my calculus sequence. I'd already taken Calc 1, 2, and 3 in Diffie Q when I took it. Basically, the class was really boring to me because uh, it was relatively easy, and all the parts of the interesting math were just sort of glossed over because nobody that's taking Introduction to Statistics has enough background to kind of handle the fact that it's actually kind of complicated, a lot of the things that are happening under the hood. When I say kind of complicated, I mean kind of complicated in like this class is kind of complicated right here. It's not really that much more than this. Or Calc 2 and Calc 3 really are required for like a full probability coverage there. So what ended up happening is a few years later, and actually I'll throw in my very brief story about this. When I was getting ready to graduate, my advisor and I sat down. To graduate, you have to have X number of credits, and you have to have all your credits done for your major, and you have to have X number of credits that are upper division credits. And we sat down filling out my forms for me to graduate, and realized that I actually only had 39 upper division credits when 40 upper division credits are required for graduation, which we had missed because we'd done a course substitution to allow a course I took at my previous college to count as a course at my current college, but we never subtracted that course from the counting when we added it in its other location there. So we were actually accidentally double counting a class from our count the year before. And so I'm sitting there like, expecting to graduate that semester and basically realized I didn't have enough credits to graduate. And so, since it was technically on a plan that had been signed off on by my advisor the year before, since he was also partly responsible, the math major and the head of the math department both failed to count up to 40 correctly. And so he felt slightly responsible for this. And so he said, okay, fine, pick a topic. We're teaching a 300 level class in it next semester. You're going to take it for one credit and you're going to graduate next semester. And I was like, deal. And so for some reason, I ended up saying, I don't know, how about probability and statistics? And he was like, done. It'll be taught next semester. Make sure you register for it. And so I did. It ended up being one of the coolest classes I took in all of undergrad. And the reason why is because it turns out that pretty much every single topic in probability and statistics depends on calculus for all of its definitions and computations, which means all that math is really skipped when you take Introduction to Statistics because it's never expected that anybody's seen calculus if you're in an Intro to Stats class. So what I am telling you is that you should seriously consider taking an upper level probability and statistics course now that you've taken all this calculus here. It was so awesome. I think the things that you can do with probability and statistics is really great. There's just not a lot of interesting things you can do until you have that calculus base, though, in this realm here. And so now that you guys do have this, recognize that this is sort of one of these fields that's opened up to you. And I also want to suggest to you guys that there are a large number of very, very good career paths that are associated with having some competency with statistics and with probability. And so, not everybody's going to be an engineer. I think that would be kind of boring, honestly. So kind of recognize that like data science is a massive career path right now. Being an actuarial science is a huge career path right now. And these are things that are very closely tied to these topics of using some calculus to make some probability and statistical computations out there. So I think today is really, really relevant to where a lot of you guys might be going in the near future. So that's kind of my like pass off advice to you guys is as you go and finish your 4 year degree somewhere else, whether it's part of your degree program or not, take an upper level class in probability and or statistics. If you've already taken intro to stats at CR, most math people that I talked to didn't like the class, and I get that. Give it a second shot now that you know a bunch of stuff. Check out what the upper level things have to offer. I found it to be one of the most fascinating classes I took in all of undergrad, so I highly recommend it. You should look into it. So my biggest disappointment today is just that we only cover this for one day and not for like an entire semester here. Um, And as my final comment before I walk away from my wall of text here is also, I taught this course last semester as well as two sections of Introduction to Statistics, and oh my gosh, is it so it teaching Intro to Stats I really appreciate teaching that class, but it is really hard for me to teach that class in the same class as I teach, or in the same semester as I teach a calculus class, because so many things come up in stats, and I'm like, oh, I want to show you guys this, and I can't, and people will ask me like really good questions, and I'm like, I can show you the math, but you can't do any of it. And it just happens like kind of all the time in that class. So really hard for me to teach this class and stats at the same time because I want to do all of the Calc 2 stuff in there and you just can't. So let's go ahead and do it. So what we want to do today is we're going to define what it means to be a probability distribution, and we are going to compute some values associated with probability distributions as well. One of the very, very important breakdowns for all probability distributions is that a probability distribution can either be discrete or continuous based on the variable that is being predicted with that probability distribution. So our most basic examples would be things like rolling a die is an event that is a discrete event because there are six possible outcomes and they are, in a sense, sort of like separated from each other, right? You get a 1, 2, 3, 4, 5, or 6. That would be following a discrete probability distribution. On the other hand, things like adult male height in the United States would be a continuous probability distribution because there's really an infinite number of values that it can take on depending on our level of precision with which we're measuring over an interval of values right there. So this distinction between discrete variables and continuous variables is a really important distinction, especially for the math that we're going to be doing here. So we're going to take a look at both here today. So probability distribution. Given an event A, such as rolling a die, we might want to know all possible outcomes, the sample space, rolling a 1, 2, 3, 4, 5, or 6. The sample space would be the set of numbers, 1, 2, 3, 4, 5, or 6. Alternatively, the event A might be, my son reaches physical maturity, right? And we want to know, can I predict 18 years from now, what will his height end up being? That would be an event, but the sample space there, I couldn't make a list. I would have to give sort of like an interval of values. And notice that for height, it's a little bit more arbitrary there. Perhaps I would set my interval to be the shortest height of a human ever up to the tallest height of a human ever might be my potential span, although technically speaking, it's obviously going to be the case in the future. I mean, almost guaranteed that we will eventually see a human shorter than the currently known shortest and the tallest known tallest. A little bit more not direct as to what our sample space might be for some of our continuous distributions. So what we're going to do is we're going to look at two very closely related and very simple examples to kind of help us build our formulas here and get some definitions out. And then once we have access to those things, we'll go look at a bit more of an interesting problem that has all the calculus stuff in it. So our example is going to be the most boring thing that we can think about in probabilities, rolling a six-sided die. What we know is that we know that this is a discrete probability distribution right here because I know that I can list all of my possible outcomes and their associated probabilities. So I want to say that this is a discrete. So this is a discrete, so X is a discrete random variable. And I would say collectively what this table makes up is a discrete probability distribution function because a probability distribution function needs to list all possible outcomes and all associated probabilities with those outcomes. So for discrete variables, it's typically the case that we state their probability distribution function, their PDF, as a table because we can list all outcomes and we can list the associated probabilities associated with those outcomes. So this table itself is the probability distribution function, is the PDF. For our continuous variables, we're going to expect to see things that are more like an equation, an f of x equals, and something in terms of x there. Right? So this table represents the probability distribution for the random variable x, where x is the outcome of one roll of a single-sided die. So what we want to do now is we want to define what does it mean to be a probability distribution function. And here are the rules, the two rules for any probability distribution function, right? These two things right here. So rules for a PDF. Right? The two rules for any probability distribution function, something is a probability distribution function if it has both of these properties right here. All the probabilities need to be between 0 and 1. This makes a whole bunch of sense to us right there. There's no such thing as a negative 20% chance of something happening. There's no such thing as a 120% chance of something happening. Every probability needs to be between 0% chance of occurring and a 100% chance of occurring. That's a really basic thing right there. The other thing is that the sum of all probabilities need to be equal to 1. All this is really saying is all possible outcomes must be accounted for, right? So if I were to say to you something like 40% of CR students drive to campus and 30% of students take the bus to campus or something like that, that's not a probability distribution function because I've only accounted for 70% of the possible outcomes as far as modality for getting to campus goes, right? So for something to qualify as a complete probability distribution function, every possible outcome must be accounted for. Another way of saying that is all 100%, that one, the number one representing 100%, all 100% of all possible outcomes have been accounted for. So my little bit of notation I might write for this is 0 is less than or equal to p sub I is less than or equal to 1. P sub I being my ith probability of the ith outcome. And the sum of all probabilities being 1, we could say is the sum of all of the p sub i's needs to be equal to 1. All 100% of all possible outcomes have been accounted for. And I guess I kind of want to state a couple more things right here. Back up here in our table, I did state a word up here that I did verbally define here. This sample space right here, the sample space is the list or a description of all possible outcomes. So this right here is our sample space. It's 1, 2, 3, 4, 5, or 6 for this particular random variable and event. And these are our probabilities that we know that are associated with rolling a six-sided die. There should be an equal 1/6 probability for each of our possible outcomes that we're going to observe right here. A moment ago, I identified a p sub I. Well, I'm kind of thinking over here, this is like, perhaps we would say this is our x sub 3 is 3, and our p sub 3 would be 1/6. Those are like just using our subscripts to indicate which of the possible events that we're referring to there. So what I want to know from you is what is the expected value of the roll of one die? If I'm going to roll a die once, what do you expect the outcome to be? And this is, I'm on purpose picking this very, very simple example because this question has a sort of surprising answer, but I think that you'll agree with it once we get it, but you're going to be, this is a big time like, wait, what? Okay, I guess I can see why that's the correct answer right there. The weird thing about this question is that since everything has an equal 1/6 probability of occurring, you should say, well, what I expect is anything could happen here, right? There seems to be an equally likely chance of anything occurring here. So it's tough for me to say what is expected right here. So here's what I want to do instead. What you should recognize is that things like 6, why isn't, okay, things like 6 have a higher value than things like 1, despite the fact that they have the same occurrence of outcome right here, 1/6 of the time. So here's what I'm going to do instead. The difficulty with this is it's difficult for me to say, what do you expect to happen with one roll of the die? Although that is our goal to answer this right now. So instead I'm going to rephrase this question slightly. The rephrased version of this question is going to be, if you rolled this die many, many times, what would you on average expect your average roll to be over many rolls of the die? Right? This is my alternate way of rephrasing this. On average, what do you expect your roll to be over many, many, many rolls? So what we're going to do for ourselves here is we're going to set ourselves up with a hypothetical situation here. Let's say pretend we roll a die 60 times. What do we expect the average roll to be? So I'm setting up a hypothetical scenario right now, sort of in a sense like a simulation, right? Where we can say what we would predict to end up seeing out there. So here's the thing that I'm thinking to myself. What I am expecting to see happen is if I rolled this die, I obviously picked the number 60 for a nice reason right here, and that there are 6 total possible outcomes associated with this guy here. And so what I'm thinking to myself is if I rolled this die 60 times, what I would expect to happen, I think the most likely thing to happen is for us to see 10 of each of our individual outcomes, right? There's 6 different outcomes that are possible that are all equally likely, spread across 60 rolls. The thing that seems most likely to me is to get 10 of each. Now, I definitely don't expect that to actually happen. I think there's a crazy tiny probability of rolling a die 60 times and getting 10 of each roll. But that's sort of what I would expect to see based on the probability distribution that's been provided to us. So what I'm thinking this would look like is I would expect to get a 10 rolls of a 1. Remember, we're looking for the average value. So 10 rolls, the value of 1, plus I'd expect to get 10 rolls times the value of 2. I'd expect to get 10 rolls with a value of 3. I'd expect to get 10 rolls rolls of a value of 4, 10 rolls of a value of 5, and 10 rolls of a value of 6. This is what I would expect to happen. But remember, we wanted to know the question, what would the average roll be? Now, since we've added up the expected values, we need to divide by the number of rolls to get the average. So I'm going to go ahead and divide this guy by 60. Now, what I want to do, since we're trying to help ourselves out and like kind of build a meaningful formula for us that we can use later, what I want to recognize right now, instead of just directly doing this computation, is that there's a really nice simplification that we can do. What I'm recognizing here is that all of these 10s might nicely divide by this 60. In fact, 10 over 60 is 1/6. 1/6 seems to be a very relevant value for me to be identifying within any computation associated with this probability distribution function. So what I'm thinking to myself is maybe we should do our simplification to look like this. I'm just going to divide all 6 of our terms here by 60, getting us to 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 plus 1/6 times 5 plus 1/6 times 6. This is going to be a really good structure for us to identify our expected values of any discrete probability distribution here. And so I think what I kind of want to do is recognize what this actually is right here. I'm going to stop for a minute and go into some color to state our general formation right here. It looks to me like this is our probability of event 1 occurring times the value that's associated with event 1. This looks like the probability of event 1 times the value of event 1 plus probability of event 2 times the value of event 2. And notice, this really looks to me like just the sum of p sub I, x sub I for our expected value. All right. So this is going to be a good formula for us to use for our expected value right here. The expected value of the random variable x is the sum of each probability of each event times the value associated with that event. Now notice, if we had one of the sides of the die had a 16 on it, we'd be using 16 out here instead as one of those value terms that's associated with this. If this were a loaded die where a 6 were actually going to come up 80% of the time, then our probability associated with the 6 would be 80%, 0.8 instead of 1/6 right there. It just happens in this case that the rolls of the die, there's 6 rolls, they take on values 1, 2, 3, 4, 5, and 6. They are all equally likely. So this is an extra simple looking example right here. But I think we can go back now to computing our answer. It looks like we're going to get a 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6. And if I add up all these numbers up on top here, 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21 over 6. And if we look to a decimal for this guy, that's actually going to be 3.5. So let's talk about this here. That seems like a weird answer to give. My question to you is, what is the expected value of the roll of one die? And I just said, I expect to get a 3.5 when I roll this die. Why does this make sense? Why doesn't this make sense? Obviously, why doesn't this make sense is because it's not a possible outcome, right? We couldn't actually get a 3.5. Why is this a sensible answer? Because the number 3.5 is the number that is on average closest to all the other the 6 outcomes that actually are associated with this probability distribution, right? 3.5 really does sit right in the middle, and it should sit right in the middle because all of our probabilities are equal to one another. This is a uniform distribution. All outcomes are equally likely. If it was the case that our large numbers were more likely than our small numbers, we would expect our expected value to be higher towards those larger numbers, and vice versa if it was towards the smaller numbers out there, right? So 3.5 is a bit weird, and it kind of bothers people when we get expected values that aren't one of our possible outcomes. But what we're really identifying here is that this is the value that is, in a sense, the center, a weighted average, the center of a weighted average right here. This was really a weighted average that we computed right here. It was just the most boring weighted average ever because everything got equal weights of 1/6. Right. So in this case right here, not a very exciting weighted average that we did because it was all equally likely stuff. But 3.5, you should convince yourself that on average over lots and lots of rolls, you do expect to get a 3.5. I think if you've played a bunch of board games before, that especially lots of board games that involve rolling two dice and adding them together, what most people know about rolling two dice and adding them together is that 7 is the most likely outcome that you can get. There's 6 out of 36 ways that you can roll a 7. That's the most possible ways for any two-sided results, any two-sided sum, right? Sorry, any two dice's sum there. And what you should notice is that 7 is the most common result for two dice. Therefore, if you divide both those numbers by 2, you get that 3.5 should be the center of a one die roll out there, the average, the expected value of rolling one die. So we've got our formula now for expected value for a discrete random variable. We did it with the roll of the die, and even though this was a really simple scenario with really simple math, it does give us a bit of a surprising answer that kind of makes us have to stop and think about how do we define this expected value term in here. So you can see the question standing at the bottom of the screen. So where's the calculus? Well, hopefully you're starting to feel out. Hopefully you're done feeling out at this point in this class that anytime we see a summation that looks like this, there is a continuous analog that's associated with that represented by an integral, right? So let's go ahead and modify our problem a little bit so that we can use that type of concept here, all right? So now in our example, we're going to do something very similar to rolling a six-sided die, but we're going to look at the continuous version of it instead. Now, instead of rolling a die, which has 6 discrete outcomes, we're going to write a computer program that's going to randomly output any value at all between 1 and 6 with equal probability. And so it's certainly the case that a computer is limited in the number of degrees accuracy that it can maintain. But we're sort of thinking that, I don't know, there's at least more than trillions of possible outcomes that our computer can distinguish between 1 and 6. And so in my mind, it's not true continuous, but it's really, really, really dang close. This is one of those things that's a little bit tough in probability, that when we label something as discrete or continuous, in a sense, because we only have an ability to measure things down to a certain number of degrees or decimals of precision, in a very, very, very technical sense, everything should be considered discrete because, there's only a trillion possible unique outcomes, so it's got to be one of those 1 trillion, so it's discrete. That's not really helpful to us. If we're thinking of rectangles that are 1/1 trillionth of a unit wide, then you're picturing area under a curve, not area underneath a set of a trillion rectangles anymore, right? So this is sort of our really lame first 3 weeks of Calc 1 where it's like, we're taking the limit as n goes to infinity. Well, let's type in n equals a billion and we're basically there, right? That's the lame version of that. That's where we're at right here, right? So what I want to know is if we're instead doing this where we're going to have a computer output literally any number between 1 and 6, continuous, like a continuous interval, what is the expected value of the output from this computer program here? So let's define a few things for ourselves. Let's define the random variable x is going to be the output from the computer program. We want to identify what kind of distribution it's following, right? So here we're going to use the notation using the little tilde symbol right there. That says the variable x, which by the way is typically written as capital letter variables here, is distributed according to the uniform distribution with bounds from a to b. This is our general notation for indicating what distribution a variable follows. So again, in English, this says the random variable x is distributed according to the uniform distribution, meaning all outcomes are equally likely, with the lower bound of A and an upper bound of B. And it's certainly the case for us in this case right here, that our random variable f is a uniform 1/6 variable right there. Any value from 1 to 6. So this is the way that a probabilist or a statistician would convey this type of information to somebody else. We'd say, I'm dealing with these variables here, and this says to me x is distributed according to a uniform distribution from 1 to 6. So unif 1/6, that's a notation for saying a variable that is uniformly distributed across all variables from 1 to 6. And so what does our probability distribution function look like? Right? Since it's a continuous function, like I expect there to be a graph that I can recognize, right? And so what I'm thinking to myself here is that a uniform distribution means All outcomes are equally likely. So if all outcomes are equally likely, then what I'm expecting to see here is that I know that my probability starts at 1 and it ends at 6. If this is going to be, so these are my x values here, and this is my probability of that x value occurring, I know that all probabilities are equally likely. So we should have one consistent probability associated with all of these here. So I'm thinking to myself, there should just be a flat line right there, right? Because all of the heights should be equal to each other, indicating that all the probabilities are equal to one another. But the question is, what is that height? Well, what I'm remembering for myself here is that the total probability that we're accounting for needs to be equal to 1. Now, what that's going to mean to me is that I just need to have the area underneath my probability distribution function to be equal to 1. That would represent all 100% of all the probabilities having been accounted for. Notice in this case right here, we have the easiest possible shape of all time. We don't have to do any calculus in this case right here because our shape is a rectangle. So our area should be, here, our width times our height. We know the area needs to be equal to 1, and I know that my width is going to be 6 minus 1, which is going to give me 5. And so it looks to me like the height of this thing should be 1/5. And that's a little bit weird here because I feel like you should be thinking to yourself something more like 1/6 based on our previous example that we did right here. But I guess let's roll with it right here. This seems to be what I would need to give myself a probability distribution function right here is this height of 1/5. So I think I've got a good graph for what's going on here. My x, my p of x, and this is a 1/5. So that seems kind of weird, but let's go ahead and use that 1/5, not 1/6 value right here. I know the width is 6 minus 1 is 5, so therefore the height needs to be 1/5. So the area underneath the probability distribution function is 1, representing the fact that all 100% of all possible outcomes have been accounted for. Um, so what our goal was here is we want to know what is the expected value of the output from this computer program. So let's kind of remind ourselves where we just were a second ago. In our discrete setting, we said that the expected value of the random variable x was going to be the sum of all the x's times the probability of x occurring. Therefore, in our continuous case, we should just basically make this an integral. Integral of the value times the probability distribution function right here, which I'll go ahead, I'm going to just call f of x right now for that curve. And each of those things, we're going to stick the dx on here, indicating the fact that there are, again, this isn't discrete. So how wide is each choice that we're making right there? It used to be a width of 1. There was one gap separating each of those, 1, 2, 3, 4, 5, and 6. Now there's an infinitely small gap between each of our two possible outcomes here. So this is our continuous analog of our discrete formula that we came up with a second ago. I'll go ahead and call that curve f of x right there. So it looks like for us to make this guy happen, we can go ahead and compute our bound and throw some bounds on here as well. We know this guy's going to go from 1 to 6. I'm going to talk in a minute about defining this f of x actually a little bit better, but let's go ahead and do this computation right here and see where we end up right here. So if I want to compute, so I want to give myself some more room, so we need to do the computation, and we want to talk a little bit more about how f of x is defined right here. Stats people have a little bit of a special notation that's actually really, really cool that I like, that I feel like I should be thrown into some other classes here. So it looks like we're going to be doing here the integral from 1 to 6 of x times, well, the f of x function is just 1/5, right? It's y equals 1/5. So this is really easy for me to do here. It looks like I'm going to get 1/5 times the integral from 1 to 6 of x dx. That's going to give me, this is going to be 1/2 x squared, so I'm going to get a 1/10 x squared, evaluated from x equals 1 to x equals 6. And if I go ahead and, oh, come on, give me some room here. If I go ahead and do this, it looks like we're going to be getting here 1/10 times 6 squared minus 1 squared, which is 1/10 of 36 minus 1. Oh my gosh, that's 1/10 of 35. Oh my gosh. So I feel really good about the answer that we just got, obviously, because it matches what we got for our discrete version right here. So 3.5 still our expected value if we know we're getting an outcome between 1 and 6 and everything's equally likely. It's not too terribly surprising because of this whole equally likely thing that our discrete and our continuous expected values matched one another right there. So it looks like we can compute the expected value for a continuous random variable here as well. So let's talk real quickly about defining the PDF. So what we saw was that f of x was equal to 1/5, but only over the interval 1 to 6, right? What's technically the slightly more appropriate way for us to actually write what our probability distribution function is? Because it's what's completely reasonable for me to say to you is, hey, real quick, what's the probability that I'll see a 7 from this computer program? And you should be able to easily tell me 0, right? Technically, that should be part of this thing right here, right? So what I'm going to say is that, so we should probably write that f of x is equal to a piecewise defined function, where it is 1/5 when 1 is less than or equal to x is less than or equal to 6, and it is 0 otherwise. By the way, this is really typical to not actually state your intervals if you're writing these in a probability class. But what's actually even a little bit more common here is to say, what's kind of unfortunate is that most probability distribution functions don't actually have a meaningful probability that you're computing all the way from negative to positive infinity, which kind of means almost every single continuous PDF is going to require a piecewise defined statement where there's 0 for all the other places where we don't have any possible things happening. But that kind of sucks. It's not like there's just a branch of math where people define literally everything as a piecewise function. Everybody knows that piecewise functions are a little bit obnoxious out there. So to eliminate the need for a piecewise function, we define an indicator function. And this is a really simple, really neat idea. So this indicator function, I of x, notice that indicator functions will always have a little descriptor underneath them of when they are on and when they are off. You should think of 1 as the on state and 0 as the off state. So this is a light switch function. It's on, it's got a value of 1 if your x value is in the stated bounds, and it's 0 if it's not within the stated bounds. This allows us to write f of x, our probability distribution function, is 1/5 times I of x 1 to 6. And I'll get lazy and just write the 1 to 6 underneath there. Okay, never mind. I'm gonna write the whole thing properly right here since I'm just introducing some notation right here. But the point is, this is a function that we can now multiply by, and it will really just tell us, is it on or off? This says you're going to notice that I of x is going to take on the value of 1 if we give it an x value of like 4. And therefore, multiplying by 1 doesn't change 1/5 at all. It's just 1/5. But now, if you plug in a number like 7 for f of x, I of 7 is 0. And so we get a probability of 0. So an indicator function is essentially an on-off switch as a piecewise function so that now we can write our PDFs in much more compact form without ever having to actually write the piecewise stuff. It just says turn this component on or turn this component off. And what ends up being really cool is when you go take your upper level probability class that you're going to take, well, you're going to realize that we can like straight up do math with these indicator functions right here. I mean, we're truly multiplying by I of x right here. And there ends up being some pretty interesting things that actually happen with our ability to use indicator functions like multiplicatively like this. So we're just multiplying by something that's either 1 or 0, meaning just keep what you got. If it's 1, everything's 0 otherwise. And that's actually a really cool idea of a way to sort of eliminate the need to ever write piecewise functions in probability and statistics. So like I said, almost like all of a probability class is going to be analyzing probability distribution functions, but really almost every meaningful probability distribution function technically needs a piecewise definition, and that's really annoying. So it's very, very common to use these multiplicative indicator functions to represent when do we actually have probability and when don't we actually have probability here. That 1/5 probability, as we saw, was something that only existed over the domain from 1 to 6. So we keep it over that interval and we let it go down to 0 everywhere else that's out there. So I think this is a really neat notational idea right there. I feel like it's something I should use more often. And in other classes, this isn't just a probability idea. It just comes up commonly in probability since there's so many piecewise functions that end up cropping up out there. Cool. Oh yeah, by the way, last thing here. It's also verbalized as saying the support. Right, so that's sometimes referred to the indicator function. The interval that's associated with it is referred to as the support of the function. It is when it is not 0. But that's just some verbalization right there. So, in general, the expected value of any probability distribution function is given by, well, we have two different formulas here. We've got in the discrete case, we've got that the expected value of the random variable x is going to be the sum of each value times its probability. And for the continuous case, we've got our integral. But the expected value of the random variable x is going to be the integral of x times f of x dx. And I'm going to leave the bounds off right there, depending on how we want to define these things. And by the way, in fact, I'm going to scroll back up to tell you why I'm not going to write bounds on this guy right now. Notice that very technically speaking, if we had properly defined this PDF right here, technically we should have just been giving these bounds on this integral from negative to positive infinity. Because from negative infinity up to 1, our true definition of the PDF would have given us 0, which is fine. From 1 to 6, we would have accumulated this much area underneath the curve. And then from 6 to infinity, our PDF would have told us it was 0. So in a technical sense here, all of our expected value computations should always go from negative infinity to positive infinity, given that our PDF is properly defined with an indicator function over its defined support. But usually that's like a little bit overkill right here. So it's completely acceptable in this case for me to just go from 1 to 6, because that's the only interval over which we were actually accumulating any probability. Everywhere else it was 0. So I just discarded that. All right, so that was cool. So now let's do the little bit more exciting stuff. Let's go ahead and identify a PDF and then find some meaningful features of it. So in this problem right here, what I'm going to do is I'm going to describe a PDF to you. I'm not going to tell you what the function is. That's going to be part 1. It's going to be your job to figure it out. And I'll also tell you this week, your homework assignment for this week is just going to be manage one of these guys right here. It's going to be a problem that's basically very, very, very similar to this one right here, where I'm just going to describe a PDF to you. Your job will be to determine what actually is the function that is associated with the probability distribution function, and then find some features associated with it. For example, what is the probability that we see an x value in a certain interval? This is sort of like me saying, given that adult male heights are normally distributed with an average height of 68 inches and a standard deviation of 2.5, 8.5 inches, what is the probability that my son grows up to be 70 inches tall? Or rather, I guess in this case, I would say between 70 and 72 inches tall. It's a probability, so we should be getting out a number between 0 and 1, between 0% and 100%. And other things that we might be interested in are finding some of our classic computed statistics associated with that random variable right there, mean, median, and mode. So let's do this thing here. So suppose we'd like to build a continuous probability distribution function, f of x, with support over the interval -2 to 4. So when we say the support is over -2 to 4, what that means is that the probabilities are 0 outside of that interval, and they're perhaps non-zero inside of this interval. This function should have a minimum at f of 0 equals 0, so it's going to touch the origin. It seems like it's going to go through that point. It's going to have a maximum at 4. It's going to grow quadratically from 0 to 4 and from 0 to -2. So basically, this is me saying it's a quadratic function. It's going to go through. It's going to go from. Oh wait, did I say the value at -2? No, we don't know where that is, but we know what the min and the max are going to be here, right? So what I know is, let's say, based on the description, it should look like, so I know that it's a quadratic. I know that the minimum of the quadratic is going to go through the origin right there. I'm going to give myself a couple of marks here. I know that it's going to be a parabola, right? It's a quadratic. And I know that it's going to go from -2 to 4, where it's non-zero. And it's going to be 0 everything outside of that. So what I'm thinking to myself is there should be some quadratic that's out there that maybe looks like this, where I know that these are sort of my end boundaries right there. And I'm going to give myself my little dashed lines right here. Now the problem is that I can't really necessarily tell what quadratic this is because I don't know what heights those points get up to right there. But at least from the description, I know it's quadratic, minimum at 0, 0, goes from -2 to 4. It experiences its maximum at 4, which must be the case given that it's quadratic right here. So what is our PDF, right? Well, I know that f of x is a quadratic, so it should be something like ax squared plus bx plus c. Since the vertex is at 0, 0, that kind of helps me know that b needs to, it's centered on the y-axis, right? We haven't been shifted left or right. So I know that b is going to have to be 0 right here. Also, because we go through the point 0, 0, I know that c is also going to have to be equal to 0. So I'm going to say centered on y-axis is going to tell me that b is equal to 0. And it passes through the origin. That's going to tell me that c must be equal to 0. So what I know is that we should have that f of x is really just some ax squared. And what I'm going to do is I'm going to indicate its support here. All right. So here is my definition of our probability distribution function. But my problem is I still don't know what a is going to be. So how are we going to find a? Well, we know that the area under any probability distribution function curve is 1, representing all 100% of all possible outcomes being accounted for. So what I'm going to do is I'm going to integrate this function, and I'm going to set it equal to 1, because that must be what we get out over the bounds from -2 to 4. That's a -2 right there, right? -2 to 4 of ax squared dx. I know that the area underneath the probability distribution function over the entirety of its bounds, over its support, is guaranteed to be 1. Otherwise, it's not a probability distribution function, because if it wasn't 1, if it's less than 1, then that means that we ignored some possible outcomes. If it's more than 1, that doesn't even make sense, because you can't have, now we're talking about our, you see all the, I don't know, I'm seeing tons of these like things on the internet where it's like, oh, there's 68% support for this candidate, 32% support for this candidate, and 91% support for this candidate. It's like, oh, so there's 190% support out there for candidate. I don't think that really makes any sense, right? So let's go ahead and do this guy right here. So this is our generally true statement for our integral from negative infinity to infinity of f of x dx needs to be equal to 1 always right here. So in our case right here, our support was only from negative 2 to 4, so those are the only bounds I'm using. Our probability distribution function is something of the form ax squared, so it looks like I can do something like 1 equals, and what are we going to get here? 1/3 a x cubed, evaluated from x equals negative 2 to x equals 4. And I can do that here. I've got a over 3 times 4 cubed minus negative 2 cubed. And that's going to give me, let's see here, 1 equals a over 3 times, and let's see, 4 cubed, 4 squared, that's going to be 64. And then negative 2 cubed is going to give me negative 8. Minus negative 8 is really plus 8. So I'm going to get a over 3 times 72. And so this is going to be giving me, it looks like I can do 3 over 72, which is really 1 over 24. Looks like that must be what a is going to be right there. So based on this, I think I can go ahead and say that our probability distribution f of x is 1/24 x squared with support from negative 2 to 4 right there. And I know that it must be 1/24 because otherwise the area underneath this curve would not be 1. And it has to be, or it's not a probability distribution function. Right? So this is kind of our way that we can find the parameter that results in this being a probability distribution function right there by taking the integral, setting it equal to 1 to say all 100% of all possible outcomes must have been accounted for underneath the curve right there. So I've now got my PDF for this guy. So now what I want to ask is, what is the probability that we would draw a randomly selected x from this distribution, and it would be between negative 1 and 2. What you should notice from this graph is it seems like the things that are the most likely are the things nearest to 4. We've got the greatest amount of probability near 4 right there. So it looks to me like if I was going to choose like a one unit wide interval that's the most likely, 3 to 4 is by far the most likely interval for us to land in that's 1 unit wide. It looks like things near 0 are our least likely outcomes to achieve. And it does look like getting things near negative 2 is also a little bit more likely, but not close to what it is from 3 to 4 over there, right? So the area underneath the curve is equal to the probability. So just a quick estimate right here. We've got this guy right here, right? Negative 2, 4. We're asking what's the probability it's between negative 1 and 2. So what we're really looking for is this area here. And it doesn't look like it's going to be very much. Right. And so what I'm thinking to myself is we can like kind of ballpark guess this thing. And I'm saying to you, what percent of all the area that's underneath this curve from negative 2 to 4, what percent of it do you think we're getting from negative 1 to 2? And it doesn't look like very, very much to me. I mean, a huge bulk of it is this stuff that's over here. And again, this stuff over here, the stuff near 0 is where we're getting very little area. So I'm thinking not much, like maybe like a tenth of the area or something like that is what we're going to end up seeing that's underneath here. So let's go ahead and check it out. So we can just find the area from negative 1 to 2 of 1/24 x squared dx. So that's going to give me 1/24 times 1/3 x cubed, evaluated from x equals 2 to x equals negative 1. And that's going to give me 1 over 72 times 2 cubed minus negative 1 cubed. And that's going to be 1 over 72 times 8 plus 1, which which is going to be 9 over 72. And 9 over 72 is 1/8. So I think we made a really good guess right there. It's a little bit more than my guess of 1/10 right there. 1/8 should be 0.125 or a 12.5% chance. And getting all of our ways to write that. I know I'm falling off the side over there. I don't think I'm missing anything right there. So we're able to compute the probability of an event occurring given the probability distribution function and the bounds of the event right there. So again, you should be thinking of this in your head as saying things like, when my son is fully grown, what is the probability that he is between 70 inches and 72 inches tall? Well, there's a normal distribution bell curve out there, and we could find the area underneath it. Actually, we can't. We're going to talk about that here in about 10 minutes. And that will be the area underneath the probability distribution function is the probability of that event occurring. So whenever you're computing a probability with a continuous probability distribution, you've just got to integrate over the bounds of interest right there. Area underneath the curve is the probability. Right? So now the one that I really like here, what's the mean, median, and mode of this distribution? So let's go ahead and talk mean first here. And our mean is our average, which we are thinking of as our expected value. Remember when we did our expected value way up here a minute ago, what we were really saying was when we said what is the expected value of the roll of one die, we rephrased this sort of as saying if we rolled the die many, many, many times, what would you expect your average roll to be? And if you average up a massive number of rolls of a six-sided die, you are going to get 3.5. So we have sort of these two different ways to kind of verbalize this as saying what's the expected value of one roll, but we're interpreting that as what is the average value of many rolls, right? And those are going to be equivalent to one another. So when we ask for things like what is the average of the distribution, what we're saying is what is the expected value of one roll of the die. Notice, we have talked about average value earlier this semester, but remember that what average value was doing was it was trying to find the correct height to build a rectangle so that the area underneath the rectangle is equal to the area underneath the curve. This is an average X value, not an average Y value. So this is a little bit different than the average value that we talked about back in chapter 6 or 7 or wherever that was, right? That would give us average height. We want the average X value that we're going to experience out here. So we've already done our expected value computation. What we remember here is that our expected value of the random variable X is the integral not of just f of x, but of x times f of x. Oh my gosh, I should just stop talking and just write so I can do it properly. Expected value of the random variable x is the integral of x times f of x dx. And we just got to put our appropriate bounds on this thing right here. So we're going to get the integral from -2 to 4, the entire support of x times 1/24 x squared dx. So I'm going to compute this as 1/24 integral from -2 to 4 of x cubed dx. And now we can go ahead and evaluate this integral here and see what we're going to get. So it looks like I'm going to be getting 1/24 times 1/4 x to the 4th evaluated from x equals -2 to x equals 4. That's going to be 1 over 96. 4 to the 4th minus -2 to the 4th. That's 1 over 96. 4 to the 4th. 4 squared is 16. 16 squared is 256. -2 to the 4th is positive, so we are actually subtracting something here. 2 to the 4th, 2 squared is 4. 4 squared is 16. So I think we're getting 240 over 96. And if we're doing 240 over 96, it turns out this is actually a really nice and clean 2.5 right there. So it looks like the average x value associated with this one, if we were going to draw one random variable from this over and over and over and over and over, what we should expect to see is approximately at 2.5, so like right there, this turned out to be our expected value right there. So that's what we should expect to see as our average roll. Knowing that 4 as a value is contributing more value than -2, not because it occurs more often, but because 4 is more of an extreme number, right? The value that we're contributing there is a larger number of 4, right? So there's where our expected value is going to lie in our distribution. And again, notice that expected value is an x value. It is not the average height of the distribution. It is what x value are we going to expect to see on average if we did this, if we drew a random variable from this distribution many, many, many times, right? So we've got our expected value of the random variable x here. So expected value of x. Now, let's talk about median, because median is very closely related to average, but uh, people make lots of mistakes with median, and we want to make sure we don't make those mistakes. So let's briefly look at an example here so that we all make sure that we see the important distinction between average and median. So what I'm going to ask you is I'm going to give you two distributions here, and we're going to ask the questions. What's the mean and what's the median? So if I give you this set of 5 numbers, 1, 2, 3, 4, 5, I could ask you what's the mean, what's the average? And we could notice here, 1, since they're evenly distributed, it should just be the middle, but we can do the math. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, divided by 5 total numbers that we added up is going to give us 3. That's the average. Now, what's the median here? Well, to compute the median, what we're really looking for is what is the middle number regardless of size. So typically when I'm computing the median, I just cross off numbers from the outside. So the outermost 2 are gone. Now the outermost 2 are gone again. And it looks like the one that's remaining in the middle is going to be 3. So you should notice here the mean and the median are equal to one another. In statistics, we would say, therefore, that this is a symmetric distribution. The mean and the median agreed with one another. Now I'm going to change these values just a little bit right here. So, new question. What's the mean and what's the mean? Or same question, I should say. What's the mean? What's the median now that 5 is instead 50? Well, it's not obvious to me at all what the mean is. I think I actually have to do the math here. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 50 is 60. 60 divided by 5 total numbers that we added up is going to give me 12. And my question to you would be, do you feel like the number 3 is a good overall descriptor of this set of numbers? And I would say the answer is yes. Do you feel like 12 is a good descriptor of this set of numbers? I have a really hard time saying yes to that. 12 isn't really close to any of the numbers here. Now, if we instead go to compute the median of this guy, though, then I can do the same game. I cross off my outermost 2, cross off my outermost 2, and I'm left with the one in the middle. The median is still 3 here. The thing that's important about the median is the median does not care about the size of the number. It cares about, instead, its location relative to the others. If you were to order all of the possible outcomes, then where does it fall in the ordering? So median is more about order. Average is more about size. Median doesn't care. We could stick 14 more zeros onto the end of this guy right here, and we're still going to get 3 for our median. It is still the middle number out of the numbers that are in the set right there. So there's our little like mean versus median distinguishing example right there. And the thing that I would argue, if I had to pick one of these two numbers and say, which of these do you feel like is a better descriptor of the data set? I would have to pick 3, I think, in this case. And that's a bit of an opinion right there instead of like a fact. But here what I would say is that this is not a symmetric distribution. This distribution has a tail off to the right because there is one value all alone off to the right, whereas the bulk of our stuff is in that 1 to 4 chunk right there. So because this is a right skewed distribution, the mean is greater than the median. Let me just say that. So I don't really care too much about this. If you've taken stats, then you'll recognize these words right now. If you haven't taken stats, I'm not too worried about that, about skew and comparing means and medians directly. These are things you'll do when you go to take your stats class that's out there later. So there's our mean and our median kind of comparison right there. So what this is saying to me is that to find my median for a continuous distribution instead of these discrete distributions is we want to say, how far in our x values should we go to get to the halfway point? And so what we're going to do is we're therefore going to define our median by saying, what x value do I need to go up to until I've seen half of all of my outcomes? right? And we're going to set up an integral that exactly goes along with this question right here. I know that my median, my lowest possible bound for the median is just whatever my lowest number is going to be. Right? So I'm going to set up an integral here from, okay, I'm going to state it in general here, from negative infinity, and I'm going to state my general one, and then we'll do the one with this problem where I'll replace this with a -2. What I want to do is I want to accumulate area up until some unknown value of m. I want to accumulate this area underneath my probability distribution function f of x. And how much area do I want to be accumulated by the time I get to the median? Half. It's the x value at which you have accumulated half of all of your area. All right. So for our purposes here, this is just going to be the integral from -2 up to m. Let me actually throw my PDF in there. Our PDF is 1/24 x squared dx, and that should be equal to 1/2. All right, so let's go ahead and do this calculation right here. So I've got a 1/24. I know that I'm integrating x squared, so I'm going to get a 1/3 x cubed evaluated from x equals -2 to x equals capital M for median, and that should be equal to 1/2. It's going to be a 1/72 times m cubed minus -2 cubed equals 1/2. So let's go ahead and multiply both sides by 72, and we'll get m cubed. What's this? -2 cubed is -8. We're subtracting -8, so that's a +8. And this should be equal to 36 since I multiplied by 72 on both sides. So therefore, m cubed is going to be 28. And our median looks like it's going to be the cube root of 28. And I can't write and say the word cube at the same time without writing a 3. 28 to the 1/3. And what do we get when we do 28 to the 1/3? Well, I already threw this into my calculator for myself here. You know that we should be getting, let's see, the cube root of 27 is 3. So we're getting a number just barely bigger than 3. So 3.037 is what I'm getting for my calculator for our median here. Or the cube root of 28 right there. So the median is the x value at which you have accumulated half of all of the area that's underneath your curve. Right? So we've got formulas now for the expected value or the average of a continuous probability distribution function. We've got the median of a probability distribution function, also an integral. Notice that these both require integrals. So again, now stop and say to yourself, dang, how does Tony ever teach intro to stats? Exactly. It's hard because all I want to do is this, except I'm not allowed to because none of them know calculus, right? So it looks like mean and median of any continuous distribution function, which is most probability distribution functions we ever talk about, require calculus to compute mean and median. That's kind of not obvious, I guess. The other one that often goes with these guys, mode is, I would say that I care 90% about mean and median and only 10% about mode right here. It's by far the one that I care the least about. For mode, you can see I just threw a whole smattering of numbers that's out here. And what I might do for the mode is make a frequency table here. And we could do things like say, what is x? What is the frequency of x? And in my table here, it looks like the numbers that I'm seeing are 2, 3, 4, and 5. And so how many of them do we see? Of the 2s, there is 1, 2, 3, 4, 5, 6, 7, 8, 9 2s. Of the 3s, there are 1, 2, 3, 4, 5, 6 3s. Of the 4s, there are 1, 2, 3, 4, 5, 6 4s. And there are 1, 2, 3, 4 5s. So it looks to me like this says to me that mode is 2. Mode is our most common outcome. It's the thing that we are most likely to see. Now, our issue is that this is a discrete example. So my question to you now is, how do we find the mode for a continuous example? So we just said that mode is the most likely to be seen outcome. So if you were to randomly draw one number from this list of numbers, what you know is that 2 is the most common, most likely outcome for you to see. Mode for a continuous distribution, well, the one that we've been looking at here looks like this. And I would say to you, given that the y-axis measures probability, right? That's our f of x axis right there. It seems like 4 is the value that has associated with it the most probability. So mode here is max over a closed interval. So either where f prime of x equal to 0 or x equals a or b. So remember in Calc 1, you guys found the max value of a function over a closed interval. What you knew that you had to check is you had to check, okay, I should just say here critical points. Because we know that critical points can occur at like discontinuities as well, and sometimes the probability distribution functions have those, right? But in any event, it should just be the highest point on the graph. Right, that's where our mode is going to be occurring right there. So mode's pretty easy right there. But again, it's calculus again. It's still the max value of a continuous function over a closed interval. So you're going to find all your critical points, and you're going to test your critical points, however many you got, as well as you know your min and your max out there, A and B. It turned out ours here wasn't at a critical point. The only critical point was at 0. But B of 4 did turn out to be the maximum possible value of the function right there. So so again, mode is even for continuous distributions. Mode is again a calculus defined quantity here. So we did some good stuff here. I've got one last thing to kind of like wrap us up, but we're essentially done. I really, really like this problem. I like the idea that we should be able to generically describe probability distribution functions without giving an equation or a graph, and you are responsible for determining what the function actually is by knowing a couple of things about how graphs of common functions work, and by knowing that the area underneath any probability distribution function is always equal to 1, and this often helps us solve for an additional parameter that's unknown with the PDF. We just defined how do we compute any probability of any interval of interest associated with the PDF by just integrating over those bounds. And we just recognize that mean, median, and mode are all three calculus-defined quantities right here. We require integration or a derivative for mode to answer all three of these guys right here. Mean and median require an integral. Mode requires a derivative. Take a derivative and set it equal to 0. Find your critical points. All of these are calculus-defined functions. And so that's why I think it's like, on the one hand, I totally get why Intro to Stats is such like a very, very like commonly taken course for undergrads with very little mathematical experience. Because as we've learned, if we've learned anything as a country in the last, gosh, I want to say last 10 years, last 5 years, last 1 year, and especially, is that people for some reason think that like science and facts aren't real, and that is completely insane. So like we need people to have a better understanding of probability and statistics, that we know things like that everybody should obviously be getting vaccinated that can and stuff like that. And I've heard some people make some arguments as to why they're not getting vaccinated, and it's very, very obvious that they're completely lacking like basic probability and statistics understanding. So more people need access to this course. So it makes sense to me that we offer probability and statistics to people that don't have the calculus background to truly do the math, because we really, really need to get that introductory level of understanding of how math relates to science, and this is how it happens. But now that all of you guys are in this place where you actually understand the calculus that underlies all this stuff, now this means that you can actually go and explore probability and statistics meaningfully, as opposed to this sort of like unfortunate kind of surface level version of it that we sort of have to give to everybody, because the cost to society is too high to just require everybody to take multiple semesters of calculus before they ever get any probability and statistics training. It's just not okay. We need more people to have that statistical background, but we just can't do the math until you guys are like right here, right now. And so you've got this now. So let's take a look at one last little thing that I think I can't ever talk about probability and calculus at the same time without bringing this up, and that is the normal distribution. I have already yelled at you guys about this a whole bunch of times this semester. And so let's talk about it one more time here, and then I'll stop. The normal distribution is defined by this horrendous looking function right here, right? This is what gives us the bell-shaped curve that everybody is familiar with, whether they've taken a stats class or not, right? So we've got our bell-shaped curve out there. This bell-shaped curve is always going to be centered at mu, mu. That's our Greek letter mu. That is for the average right there, and that we're always going to be traveling one standard deviation. We always kind of like mark this thing off with more lines. That's one standard deviation to the right and left of the average, and there's a bunch of these that are out there, right? So what special calculus statements can we make here? Well, since this is our probability distribution function, what we want to be able to do is, for example, find area underneath the curve. This is exactly what I'm talking about. Where if I were to ask you the question, what is the probability that my son grows up to be between average height and one standard deviation above average height? Well, to do that, I'd want to integrate this function from mu to mu plus sigma. Well, huge bummer here. The huge bummer here is that what you can see is strip away all the crap from this equation, all the constants that don't matter to you. What you can see is that this equation is basically e to the negative x squared. That's the meat of this. If I get rid of all the constants that are out there that don't affect my integration, this is the function e to the negative x squared, and we cannot integrate that. There is no antiderivative for e to the negative x squared. So the hugest bummer in like all of probability and statistics is that the most commonly used and studied probability distribution that there is, the normal distribution, the thing that like the central limit theorem says that all sampling distributions are going to converge towards. We literally can't actually do the calculus associated with this one. It's a huge bummer. It's like the one that we want and we can't get it. This is why in probability and statistics you just look up a bunch of these values in a table or you get them out of your calculator. Turns out your calculator is just doing Simpson's rule underneath this curve right here. It can't actually come up with any exact answers, right? So what we're given here is that these values of mu and sigma that you see in this equation, they are average and standard deviation. But how are they really defined? Oh, I can get this graph up here, right? Here's my much nicer version of this thing. Come on up, come on up. There we go. So how are average and standard deviation actually defined? So I'm going to do a smidge of math right here real quick, and I'm going to show you one thing. Well, how do I know where mu is at for the average for the normal distribution? Well, the kind of obvious thing that you calculus students should recognize is it seems to be the x value of where we reach our maximum value. So you should notice that when we take our derivative with respect to x of this f of x function here, we're going to get all of our, we know that since it's the derivative of an exponential, we're going to get all of the original parts back times the derivative of the inside function. The derivative of the inside function is this guy here. So it looks like this 2 is going to come down and cancel with the 1/2. The negative survives, and we get the x minus mu over sigma. And we can set this equal to 0 and solve to find out where that value is going to be occurring. And you should notice this gives us no roots because it's an exponential. This gives us x equals mu as the place where we're going to reach our maximum value. So to even prove that we reach this maximum value, the average, the center of our normal distributions at mu, it requires us to take a derivative and set it equal to 0. Now, what about the standard deviation? How do we define the standard deviation? Well, you should stare at this graph for a moment and tell me what you remember from Calc 1 does it look like is happening at one standard deviation away from the average. So here's our average at mu. And you can see we're going 1 standard deviation, 2 standard deviation, 3 standard deviations above average right here. Down here, you can see they're giving us what are our estimated probabilities right here for any normal distribution, whether we have a huge standard deviation or whether we have a tiny standard deviation or whether our average is over here or over here. It's always going to be the case that we're going to see in stats, this is referred to as the 68, 95, 99.7 rule. It's the empirical rule. And this is our way to estimate for what probability of events fall within 1, 2, or 3 standard deviations from average. What you can kind of see here is that almost all outcomes for anything that's normally distributed fall, 99.7% of all outcomes are between 3 standard deviations below and 3 standard deviations above, stuff like that. So it's typically the case that we only kind of talk to within 3 standard deviations out there because that's basically everything out there. We're only missing about 0.3% of all possible outcomes out there. So my graphical question to you is this. This is a graphical Calc 1 question. What is the thing that is happening graphically at this x value right here? Or maybe you should be looking at this location right here. What's the thing that's happening right here graphically and right here graphically that's special? I'm going to mark this point as well. What's going on here? Well, what you should be noticing graphically about this is that our curve here is clearly concave down in the middle, but our curve is clearly concave up in the tails. And where does it switch concavity? Right here. So I'm not going to take a second derivative of this guy right now because I don't really care to do that. But if you were to take a second derivative of this function right here, you're going to end up finding that mu plus sigma is the locate when you set it equal to 0 and solve is exactly going to be what you're going to find. This is where we get our inflection point, right? So even standard deviation is another thing where we can't define this without calculus, at least in terms of the normal distribution right here. The normal distribution, if you take two derivatives and set it equal to 0, what you're going to find is mu plus sigma, one standard deviation above or below the average that's out there. So this is really cool. So again, this is sort of our justification for you today that like every single probability and statistics word you've ever used when associated with a continuous probability distribution function is actually a calculus definition. Mean, median, mode, expected value, average, standard deviation, all of these require calculus for us to actually be able to discuss them, which just is not. I mean, I'm like pretty positive that none of you kind of like felt that way before this. And now this is, I think, hopefully opens your eyes to realize this is a way cooler topic than all of you that have taken intro to stats and not liked it probably realized in that class, because we have to skip over all this stuff because nobody knows calculus yet. So your primary homework problem for this week, by the way, is going to essentially be like this guy right here. I'm going to describe to you a probability distribution function. You're going to have to do some work to figure out how to build it in a way that makes sense. This is actually going to be, this one was kind of easy right here. The one I'm going to give you in the homework is going to be a little bit tougher than this. And then I'm going to ask you for some questions like what's the probability of an event occurring, mean, median, mode, stuff like that. So your homework question for the week is going to be one that's a lot like this guy right here. So look for that. That's all I have for you guys today for probability. So where are we coming up next? Let me just talk through this thing real quick right here. Chapter 9 is the chapter on differential equations. That's an entire class that you guys are going to take next year. You should really do it. Differential equations, it's like, man, this is the hardest of the calculus classes, and the reason you need to know all this is so that you can be successful in Calc 3 and DiffEq. DiffEq is just like, look at all the amazing stuff that you can do now that you know Calc 2. So you should definitely do that. So chapter 9 is really its own whole class that you'll take later, which is why we're skipping chapter 9. In chapter 10, what we're going to do is we're going to visit parametric equations briefly, where instead of defining y as a function of x, we're going to define both x and y as functions of t, which we typically think of as time. We're going to see what kind of curves they draw out in space, and very importantly, we're going to want to do calculus on parametrically defined curves as opposed to traditional function expressions, y equals f of x. And so the really cool part about this is we're just going to sort of like make sure that we're all down with what it's like to be a parametric function. And then we're just going to revisit a bunch of topics such as arc length, surface area, stuff like that. If we have parametrically defined equations, or if our curve is parametrically defined, can we still compute all these things of interest that we saw back in chapter 7, chapter 8. So it's going to be sort of like revisiting old topics, but with a new setting as to how we define our functions out there. So I really like these. That'll be a cool week next week. And then after that, we're going to go ahead and dig ourselves into chapter 11, which is our big, meaty wrap up to this semester here. So we're in our last third of the semester. We're ready to kind of cruise on into our major final topics out here. So chapter 10 stuff is what we're going to cover a little bit next week, and then we're going to get on to chapter 11. So I will see you guys next week for chapter 10. Have a good one, everybody.